Yeah, g'day and welcome back to my channel. This week I'm back working on my replica of a 1920 Redrup Radial motorbike engine, and it's all about the cylinder heads. So now that the pistons are progressing along, I turn my attention to the next simple and easy to define component, the cylinder head. The Redrup Radial, being a side valve engine, has a very simple cylinder head. It's just a single piece casting with some cooling fins and a spark plug boss. At first glance, the 3D sketch would lead one to expect a simple casting with a split line on the bottom of the casting at the cooling fin. However, the more detailed section view I'm working off indicates there's one complete cooling fin with the interface to the cylinder being lower down in the gap between fins. Now there's a few ways of addressing this in the casting. I could do a split pattern, I could cope down to a lowered split line, or I could use a following board. But in this case, I think I'll just use a split pattern. It's generally the easiest for me. As soon as I started modeling, I encountered the first issue of missing information. Looking at the cross-sectional view, we know that the bore is 2 inches and the inlet and outlet ports are 13/16 diameter. But what is unclear is whether the combustion chamber is formed by the tangent of the circles to give a sort of attractive lozenge sort of shape, or whether the port width is carried through to the chamber. Now that's a significant difference, as it will also affect the compression ratio. Now, since it's a 2-inch bore with a 2-inch stroke, which is sometimes called a square cylinder design, the piston swept volume is 103 cubic centimeters. Using CAD models, the lozenge-shaped chamber is 26.5 cubic centimeters, while the smaller one is about 4 cc's less at 22.4. That bumps the compression ratio from about 4.9 to 1 on the lozenge shape up to 5.6 to 1 on the alternative. Now the only thing I know about fuels from the early 20th century comes from a discussion I had with Coleman Meyerhofer of Craft Lab. I'll leave a link, cool company. His company restored a 1917 Austro-Daimler 6-cylinder aircraft engine back to airworthiness and flew the thing in a Hansen-Brandenburg C3 aircraft. The original Imperial War Ministry contract for the engine defined performance guarantees for sweet fuel and sour fuel. Coleman had done extensive archival research and came to the conclusion that the sweet fuel would have been somewhere in the range of, I think he said, 60 octane, with the sour fuel significantly below that. Now, given that the only gasolines readily available today are 87 octane and upwards, and also that I can easily modify heads to machine out more volume to lower the compression ratio, but would have to redo the castings to reduce it, I've decided to make my replica heads with the smaller high compression chamber shape. Now the more I get into this project, the more impressed I am by Charles Redrup. Although from a professional family in Barry, Wales, and having attended a private school, he left school at 14 to commence a 5-year premium engineering apprenticeship at the Great Western Railroads. The apprenticeship syllabus must have been an excellent one, considering the quality of his draftsmanship, experience with all aspects of casting, machining, and design skills. I first went down a rabbit hole of making the cooling fin a lozenge shape as the one shown in that one sketch. So I've been using CAD for decades, but I'm no way a power user. Most of my designs have been pretty simple geometries and assemblies of only a limited number of parts. I've rarely used lofts, but I decided to try them to get that lozenge shape, cooling fin shape. Took a fair bit of playing around, a lot of failed starts. Once I got one half of the cylinder head lofted, I could then mirror it and it seemed to look okay. But all of the time, I was considering how attractive it is to just go to the wood shop and start sawing, planing, gluing and sanding up a pattern. But after watching a bunch of FreeCAD how-to videos and a fair bit of frustration, I finally got to this point. I then went through the battle of trying to fillet it. Now the filleting function of FreeCAD to get sort of root radiuses on all these fins and stuff, it's not that robust, especially because everything has to have a draft angle as well to be able to pull things out of the sand. You end up with a lot of non-right angle joints, which FreeCAD's supposed to put fillets between. I guess FreeCAD is very intolerant of sloppy drawing, whereas I'm very intolerant of rigor. With that done, the focus moved to the top cooling fins. Here, my initial pattern had 7 cooling fins. Various photos and sketches demonstrate that Redrup changed its design a few times. The earliest industrial engines only have 4 head fins. The sketch has 7 fins, but the motorbike engines appear to have 5 cooling fins. So that's what I'm going to go with. With the cooling fins done, next up is the spark plug boss. I googled spark plug thread specifications, and as often the case, the great thing about norms is that there's so many to choose between. Digging a bit deeper, it looks like British motorbikes all used 18mm spark plugs up until the 1940s, when the smaller 14mm plugs became more common. This kind of matches up with the comically large size of the plugs seen in all of the photos of the Redrup engine. This of course led to the next temptation to deviate from the original and switch to modern 10mm plugs even, which would be a better visual match to this engine size. But no, temptations to be resisted. Big plugs, it's gonna be. Consulting my modern motorbike mechanics, which was given to me by my dad and is way too modern, as this is the 1965 5th edition, the standard length of 18mm spark plugs is a 1/2 inch. And sure enough, that seems like that's still a common size today, as I was able to buy this Champion D18 spark plug with no issues. Now unfortunately, the section drawing, which is kind of my master, does not include the plugs or the plug boss. Going through all the photos, I'm guessing that the plug comes out at a 45-degree angle and is roughly located above the inlet valve. It looks like that boss has an undercut under the lower edge, so to be able to remove the pattern from the mold, I'm going to need a loose pattern part. Okay, at this point we have all of the features which form the casting pattern, so I'll clone the model twice and split it into an upper and lower pattern. Well, that's what I thought I'd do, but unfortunately the model had collected a few errors, so when I exported it as an STL file, the Bamboo Lab slicer wouldn't accept it. However, it does pop up with a useful hint to use the online Formware STL repair tool. That works great. I'm really glad Formware provides that magic program, which seems to fix anything you send it. I sent them a donation to thank them for that. However, it's nice to see that the Bamboo Lab slicer also includes a function to split a model at a user-defined level, so that addressed the problem I couldn't get FreeCAD to do for me with my partially broken model. So after I printed my first design attempt at a cylinder head, although I like the lozenge-shaped cooling fin look, the reality finally hit me that I've seen no evidence that that was used on any of the Redrup Radials that were actually built. All the photos of motorbikes and stationary industrial engines all show round cooling fins. So I scrapped the initial design and started over, drafting 2-directional extrude onto the main solid and then a revolve to make the rib. I'm surprised FreeCAD cannot fillet that cooling rib onto that head. With some help from friends, we tried this out in 5 different CAD programs and 4 of them could fillet it. Some of them really easily with just like a single click. Some of them needed a little more like clicking around the intersection line, but all could do it. So I did a Patreon members live stream on that issue. I got a mate at work who actually teaches CAD at a local polytech, and I knew that they used CATIA. All he needed to do, I think, was just select a single point in the, along that intersection on each side, and it filled it. It found the rest of the geometry on its own, which is kind of what I would have expected. One of my daughters has SolidWorks on her computer from the university. This is the same part, exactly the same task. I think she needed to go right along the intersection line. But as you can see, it looks like it's probably already found the rest of the way by there. She probably wouldn't have needed to go and click all that way along. But once again, the program has no problems whatsoever to find what it needs to do and to extend that path right along. Next up here, we've got Inventor. I always thought Inventor was the prettiest of the CAD interfaces. I think I might have mentioned once I was on the world's most pointless business trip where I was sent to Seattle for a whole week to learn a software to read out flight data recorders, which I knew I was never ever going to need to do that job. But the Honeywell training center had Inventor on it, so I spent the whole week playing around with Inventor. Kind of taught myself using all their tutorials. It was a great week from that point of view, so I guess it wasn't the most useless ever. Next up, we have got Onshape. I did this in Onshape, and what I found was just if I only selected a single part of the intersection, the first thing it tried to do was extend it around the part in the wrong, like around the whole part. Once I started picking lines around the corner, it went around the corner on one end, but still headed off in the wrong direction around the second end of the rib. And there we go. Once I sort of moved along, selecting more pieces of the intersection, sooner or later it actually worked out what I wanted to do, and then it was fine. And lastly, in FreeCAD, I've tried clicking on just one point of the intersection and selecting fillet. It errored out straight away. Then I tried going around the entire intersection, chaining the whole thing together, and once again pushing the fillet button, but the result was the same. Yes, you've got draft angle above and below. Yes, this also has draft angle on it, but the actual intersection line seemed to me to be a pretty clear and obvious line. It doesn't bound up to any other facets or anything like that. So I really don't know why FreeCAD struggles with it so much. Now here I've switched to the round cooling fin, and at the same time I also switched to printing with ASA. ASA is a bit more tricky to print than PLA. It shrinks quite a bit, and therefore if it's not perfectly adhered, then you get, lift off the build plate. You can see I used glue stick, which works really well, but I stopped my glue stick here, so that was on me. Same on this one. There's a corner that's curled up because there was no glue stick there. Because this is scrap, I'll use this as a test piece for smoothing with acetone. Now, if I understand it correctly, acetone is heavier than air, so either you're going to need some sort of a setup where the fumes get circulated around with a fan, or I've seen this method used where just stick it down with magnets and then flick that upside down, and the part just gets to sit in this acetone environment for about 20 minutes, if I understand it correctly. Let's give it a bit more, let that soak in a bit, and 20 minutes. Right, it's now been 25 minutes. Okay, my first impression would be that it's softened a bit, but it hasn't really run together yet. So I guess I'll need a little bit longer next time I try this.
Tomorrow.
Right, I left this part in acetone overnight. It's now been, it must be 9 hours later roughly. Let's have a look. Okay, that's too much. That's way too much. It's good to know the limits of this procedure. I've decided to do a comparison of an acetone smooth pattern with a pattern straight off the printer. Obviously, when you do these very, very flat angled portions like this, you're always going to have quite obvious layer lines. Not much you can do about that. I do really notice that the layer lines of the more vertical parts really have become extremely smooth. Maybe it'll help with them. On the other hand, there is a little bit of distortion, so these don't touch perfectly. That may or may not really matter because there's going to be the weight of sand pressing on those kind of flexible flanges anyway. And the last issue, of course, is that there's been a bit of rounding of this edge here. So the first casting session is going to show whether we get the smooth pattern pulling from the mold better, and also if we get more flashing around the split line due to rounding. I have to have this little loose pattern piece here, and I can't have that pull out of the sand when I pull this piece of the pattern. So I think I'll drill a hole through the base here, so I can use like a piece of wire or something to hold that firmly in the sand at its angle, and then I can pull this loose piece out along its axis, if that makes sense. Stop. I did my first casting attempt on the cylinder heads back when I was still working on the pistons. If you didn't catch the 5 videos on those, there's a playlist, so I'll leave a link. This first cylinder head casting attempt was also done before I got into contact with Martin, the old foundryman here on YouTube. So my casting practice here is pretty ropey. It got a lot better once Martin started coaching me. My sand mull is kind of small, so I have to keep mulling my sand in small batches, but that's okay. This was also shot before I made the pouring shank for this size crucible, so it was a bit dodgy the way I was holding it. Success kind of looks different. None of these castings completely filled. The reason for that is I poured too cold, and the reason I poured too cold, I just had to guess the temperature and I guessed too cold. But so these are the two that were cast together as a pair. You can see how I didn't pull the little extra plug piece out on this one nicely, and also probably got some sand wash or something falling into there. I'm guessing that's what caused that defect. The fins didn't completely fill, even though they're on the bottom and would had the highest head of pressure. I don't really see much difference between the one that was acetone smoothed and the one that wasn't. I think this was the smoothed one. I don't really like the look of this striation across here, so I think I'm gonna body fill and paint the pattern to hide that striation. Yeah, I've got quite a few defects here with the combustion chamber not releasing from the mold nicely, and of course the fins didn't fill completely. Quite a few little either air bubbles or just little defects all over. All in all, not great. This is the third one. This is the one that was done on its own. It was also the last part to be cast, so it had the coldest metal. On this I nearly managed to get that spark plug boss to pull cleanly, but took it a bit of a breakout. I need to have a think about how I'm going to do that properly. This one I did actually manage to pull the combustion chamber cleanly. I don't think I'll bother using the acetone vapor smoothing for this job. It's not really that effective. Hey, since FreeCAD refused to make that fillet, I finished up the rest of the model and left that fillet for bondo. It's really not a big burden. I'm going to need to bondo and sand the fins anyway to hide the layer lines, because I do want this looking like it was done back in 1920. Anything that screams 3D print really doesn't fit to that whole sort of gestalt. I have that shallow draft angle on the horizontal fin, so the layer lines are very prominent. I actually switched to the thinnest layer, highest quality, which Bamboo Labs X1 Carbon will support. That's a 0.08 layer line, and for all of the following patterns, that's what I'm going to use. Right, with the pattern now prepared, I've also kind of realized that if I just cast these like that, I don't have any good way to fixture them, because I'm going to need machining on this face. I need to drill and counter bore holes here, and then I need to tilt it and do the spark plug thread. So what I think I'll do is make up two little blocks, cast onto the ends of it, which will pack the thing up and allow me to fixture it. And then once all those things have been machined, then I can just machine those blocks off. Now, speaking of head retention screws, it seems that Redrup like to use a lot of small screws. I'm pretty sure these are going to be 3/16 by 9/16 long British Standard Fine, and that's the closest match with the cutaway dimensions. The weird thing is I can't find a table anywhere which lists a cross flat size for 3/16 BSF hex head screws. So for now I've modeled kind of a 9mm counter bore, because if I use hex head screws I'm going to need some space for a socket to get down around the screw head. But if any of you actually owns any 3/16 BSF hex head screws, please measure the hex across flats and let me know in the comments what size that is. Then again, looking closer in the photos, maybe he just used slotted headed screws. Now we're jumping forward nearly half a year, as the pistons turned out to be a much longer job than I expected. I'm starting to suspect that my rough plan of about a year and a half to make this engine is going to end up taking more like 5 years. And I really do love this printer. Compared to my old home build, this just works. So these were printed in PET-G. First thing I need to do is just take out the combustion chamber. Give that a little bit of a sand down. I've printed this in PET-G because I was told it sands best. Alright, now because I hit the wall with the filleting algorithms of FreeCAD, I'm missing fillets around this bit. And also, although I was able to fillet everything around here, once I got to this loose pattern part, which gets pulled out of the sand separately, I of course couldn't fillet around this bit. And because I'd like these fillets to end up with a nice even radius, I need to make myself a little tool. So for that I'm going to need a ball bearing. Yeah, that should do it. Just under 3mm radius. And I've just got a bit of steel wire. I can braze those two together to make my filleting tool. I'll use a bit of this flux. Now the solder I'm using is very high silver content brazing wire. It's pretty expensive, but you only use bugger all of it, so it doesn't matter. Right, that should do the trick. If I'm going to get a fillet round under the base of this but still have it removable, I'm going to have to make sure that the bondo doesn't stick to this, so I'm going to give it a coating of wax. Now because my first versions of this model had the interface between these two parts pulling up parallel to the spark plug hole, it meant that theoretically I'd have to try and pull the whole pattern out of the sand at that angle to disconnect the two parts. Now that obviously didn't work. For the next model, the disconnect between the loose pattern and the main pattern being effectively vertical. So the main pattern can pull straight up out of the mold, leaving the loose part in, and then the loose part can get pulled out along its axis. This is my immersion thermometer for testing the temperature of the molten aluminium before I cast it. Aluminium absorbs quite a bit of hydrogen when it's melted, and that hydrogen fizzes out of the mix as it hardens, making bubbles, so you want to try and avoid that. So you really want to pour at the lowest temperature you can. For a big casting you might get away with a pouring temperature of 680. For a thin and difficult one you may need to go up, I don't know, 720, 740. I don't know what the experts would say on that. So inside there's just a standard K-type thermocouple, and you don't really want that metal getting dissolved by the molten aluminium. By the way, that's not that different to the way temperature measurement is done on jet engines. Now ideally you'd be measuring the turbine inlet temperature at the first stage high pressure nozzle, but unfortunately the temperature there is normally significantly above the melting point of basically any usable metal. So these first stage turbine blades can only survive that temperature because high pressure air is being forced into the root of the blade and then comes out through these film cooling holes and effectively causes an air bubble of cooler air. I mean, it's not cold, it's still air that's gone through the entire compression process, but it hasn't gone through the combustor. This high pressure, relatively hot air is used to build a cooling bubble to keep the flow path gas from impinging directly onto the metal surface. And secondary protection is this kind of white ceramic coating that's on the high pressure turbine blades. On this scrap blade, you can see that one of those film cooling holes has probably become clogged. And as soon as that becomes clogged, it leads to loss of that nice cooling air bubble, impingement of the really hot combusted air, and the blade starts cracking and deteriorating. This can sometimes be caused by bird strikes. Small birds like sparrows don't normally do any damage to an engine unless they've got stones in their gizzard. But the puff of blood, as they're chopped into a gazillion little pieces, can go through the internal air passages, up through into like a blade, and then clog up one of these film cooling holes. And that is quite a common sort of damage you'll see at a shop visit. So you want to measure this temperature, but you can't because you'd melt the probe. So you've got to move further back to find a spot where it's still hot enough to get useful temperatures, but the probes can survive. The probes will be more sophisticated than this. They'll also be probably K-type thermocouples, but there'll be two separate measuring elements in each probe, one going to each channel of the engine controller. As the pressure ratios have risen and these temperatures have got hotter and hotter, these thermocouples have been pushed further and further back into the engine. Like on the GE90, the EGT thermocouples are actually below the low pressure turbine. But what GE did for that engine was to try a pyrometer, which is a sapphire lensed optical device, which is basically looking at the first stage of the low pressure turbine and looking at how red it's glowing. So the light gets transmitted down a fiber optic light guide to an infrared sensing, effectively, color temperature meter, and color temperature of the first stage turbine is used as a proxy for turbine inlet temperature. So to protect it, I made the sheath out of graphite rod. So I think that's working okay. And also I'm pretty happy with the handle that I made for it. But unfortunately, when I first built it, I sort of just got to the point of needing it and bodged the measuring thingy with a bit of tape. I mean, I did use electrical tape, so it wasn't like it was low quality or anything. But now I've finally gotten around to actually designing and printing up a couple of holders to clamp this thing and bolt onto the tube. Alright, that looks more like it. The aim of today's casting session is just to test my pattern, see whether I can pull it out of the sand nicely or whether I need to do some more modification on it. Designed this so that the fins are going to be cast face down in the drag. I can already see here that those little slots are probably going to be problematic features. I'm not sure if they're going to work or not. Better put the second part of the pattern in first, shouldn't I? At least I had enough parting powder there so that it didn't stick. Maybe too much. Well, first up, on the cope, those little pieces came out quite nicely. I've definitely got some damage across here. That corresponds to this bit across here. Now I'm wondering whether that's really a defect from that, or maybe the sand really was just a little bit too dry. Looks like I might have rammed the drag a bit too soft because there's quite a few indentations and stuff in it. So next time I ram it, I'll do that a bit harder. I've just realized that I don't actually have any lifting points in this. Let's just try this as a starter. But I'll drill 2 holes in here so I can screw screws into it. Oh, okay. That piece was supposed to stay in there. Well, I think I'll also drill a hole in here so I can just break that little grip that it gets there. Otherwise, the rest of it looks pretty reasonable. The fins are looking great. I'll drop that mould back into the muller and add just a little bit more moisture to the sand and go inside and drill those holes into the pattern and give it another go. Right, second attempt. Okay, this is not looking too bad. I'll use a bit of cylinder head and my previous attempts. Oh bugger, I ran out of gas before it melted. Man, when did gas get so expensive? I had a serious brain fade on this pour. I somehow managed to reset my expected temperature by a whole 100 degrees. So I thought 650 was too hot and waited till it cooled down to 600 before I started the pour. Should have been 700. Right, well, although neither of them filled completely, I do consider that session kind of a success in that I was able to mold those bosses without any bits falling out. One of the errors I definitely made was having the ingate on the thin side. I should definitely be feeding through that boss. I've also realized I'm probably going to need some sort of a shrink bob to prevent shrink defects. That feature through there seems to work okay. So that should give me my clamping. So I'm pretty happy about that. Also worked on this one. My general casting cleanliness is massively improved. That sand gives a reasonably rough texture. The changes on this version 3.4 So the thickest bit of the casting that's going to have the most shrinkage is here. So the idea, because that's printed upside down is I'll put a feeder above that, feeding through this thick area here. I hope that's enough to work as a feeder, and I hope it's also aligned well enough. Not that certain that that's going to work. We'll give that a go. I didn't bother filming up to this point because you've already seen that a number of times. But now let's look at the changes I made. So once again, I'm feeding down to that like fixturing block on the end. But now I've got my riser here. This is just an air vent on the opposite side, also on that fixturing block. Right, now let's try my new cookie cutters, which are going to be used to make the pouring basin. This one should go down 20 millimeters. This will go down 25, leaving a little lip in between. I can form the lip with the brush. That was supposed to stay on the top, it fell in. I've now lost a piece of my combustion chamber. Just push down on the loose part a bit and tap and loosen the rest of the... Looks good. Okay, that failed. That stuck on too hard there as well, damaging through this part. Not a super easy mold to make. I think my sand might have been a little bit dry on this bottom part. I mean, it looks nice, but maybe a little more green strength might have helped there. Okay, so I'll drop that out, remull the sand, and start again. Right, here's attempt number 2. All right, that's looking really good, I think. Pretty close to perfect. Right, let's take a look at the other side. Around this piece here is also going to get machined away. So I can also just take off that sharp edge to stop sand grains falling in. Right, with 2 molds now prepared, let's get some melting going. Right, let's take a closer look at those. First thing I can see is there's no obvious shrink defect or anything around the spark plug boss. That riser's obviously done its job nicely. So this was poured at 680 degrees Celsius and it got very close to filling. Just a little bit on that second fin here that didn't quite make it. So next time I guess I'll go up to maybe 700, 690, 700, something like that. But all in all, I'm pretty happy with how that's developing. And that probably 10 degrees that I lost between the first and second pours was enough to cut down the amount that this fin filled. Once again, got no defects at all around the spark plug boss, so I'm really happy with that. I know there's a very small one under there, making good progress. When I first measured it, it was only 650 degrees, so I put the gas back on to heat it up to my target of about 700. Notice how I don't control the pour here very well, and some of the metal overflows from the pouring basin and goes down the feeder. Now one of these two actually filled the fin completely. I think it's the second one. When I showed Martin, the old foundryman, a photo of this, he immediately identified that maybe it only filled because of the extra flow down the feeder. He recommends an even higher temperature. The surface tension of aluminium obviously sinks as the temperature rises, so the hotter you get the melt, the more it takes the texture of the sand. So you really want to try and pour at the lowest possible temperature. Plus my sand is reasonably coarse, so that's leaving this relatively rough surface finish. The second issue is the hotter you get it, the more likely you are to get porosity. I'm not sure if that was porosity. I think it's more likely just to be individual loose sand grains. The one thing I could still try to improve the surface finish would be to switch from my water-bound green sand to Petrobond or oil-bound sand. That is generally a much finer sand grain and gives you generally a better surface finish. So I might try that out, although that has the danger of picking up the striations from the 3D printing, especially here on the top surface. And because this is supposed to be a replica of a 1920s engine, I'm trying to avoid any obvious 3D printing sort of aspects to it. You can see I'm getting a little bit of a mismatch through here. I also had a little bit of sand damage to that fillet when I pulled the loose part, and this was still done with my old pattern, which has this gap between the two feeder extensions, which I turned into just a single slab feeder. So I just need to finish up this final pattern because I'm kind of hoping that I'll be able to cast two of these in a single flask to speed up the production of more castings. Right, well there we go. I now have two cylinder heads, at least good enough to practice machining on. This one, of course, is going to be my first machining test dummy. Seeing that it's slightly missing a bit, then I can move on to this one. So make sure you hit the subscribe button because then you'll get notification from YouTube when I put out those videos on the machining and on the mass production of these cylinder heads. Thanks a lot for watching.